so let's get started. Welcome back. So I know you're all excited about your projects, so but just hold off a little bit. So firstly, we're going to talk about some random projections, which is a really cool technique. Let me start by going over the schedule. So the second half of class, you should turn in your intermediate reports on Canvas and brought some printouts, because in the second half of class today, you're going to be meeting with other groups. I'll put up the plan for the meeting with other groups and so shortly, and you'll see which groups you're going to be paired with, and I'll mention that then. Also, you should have, hopefully, most of you have signed up for a time to meet with me. Have your project group meet with me individually for these meetings of like 7 minutes. From talking with Madi, it seems like for the times that were right after class today, there was like an hour block. It seems like there was trouble signing up with those, so there might still be some availability at those times. If your group would like to meet with me after class today, or if you send email to Madia, then he can arrange the schedule. So, okay. I think there are kind of barely enough spots for groups. So if you don't sign up once today, then groups might not get a slot later. If there's a reason why you can't go in any of those slots, that's quite possible. Then contact me and Madia, and we can open up some spots. They'll just be a little bit later. I basically took all my free time starting from now until next Monday and filled it up with sign-up slots, but I can add more after that, so you just have to wait a little bit longer. Okay. So the other thing, notice the regression homework has been up for a couple weeks now. It's now due it's now due in a week. The homework was designed to be done in fairly easily in MATLAB. I basically gave you most of the commands I asked you to run. You can do Octave. So MATLAB is installed on Cave. I know you have to pay for MATLAB. It's installed on CADE, so you can access it that way. You can also use Octave, which is the free alternative, and that should work just as well. I also gave some simple instructions on how to load the file into Python. If you'd prefer to in Python, that's also fine. These last three assignments are basically just, they're matrix operations, and so I've just for historical reasons, I have them written up to be done inside of MATLAB, but you're welcome to do them in Python if you feel more, or any other language if you feel more comfortable with them. The dimensional reduction homework should be up soon. We're finalizing the data set on that one. It's due 2 weeks from today, so hopefully we'll have up later tonight, maybe tomorrow. I figure you probably aren't that eager to start on it tonight, so hopefully if we get up tomorrow, that's still okay. And remember, when you come to the meeting with me, if not all of your group can make it, this is, that's probably fine, but hopefully you can make it. You should bring printouts of your data collection report, your project proposal, and the intermediate report, and I will try and read it while I'm giving you feedback then. That's the reason in order to do that. Come prepared with those. Please try and be on time so we can keep things moving. And the goal of it for you should be asking, before you come in, what do I need to do to finish the project, right? So if I haven't answered that by the time we're almost out of time, then you should maybe try and remind me, what should I do before the end? I'll try and tell you that, but if not, that's what you should be getting out of this. So okay, great. So we're in the dimensionality reduction phase of the class. Talked a little bit about that Monday, basically a review of the singular value decomposition and PCA. We're going to give a fairly completely different approach today. One more thing I want to mention: there's this, so there's the Data Science Club. I don't know if you know about it. You can go to this website and sign up and find out more. They're putting on an event tomorrow at 4:30. There's a talk by a local grad student that's maybe of interest to you guys. So pretty informal event. Just here's an advertising. It's going to be in Web 2250, 4:30. So tomorrow. Okay. Great. So so random projections. Okay. So let's start. Let's review. Kind of our input is going to be n. So data points. We'll think of them as A1, A2, up to AN. Each AI is going to be in RD. So one way of thinking about this is going to be this matrix A. We'll think of n as being large, and just because we always think of the size of our data as being large, that's when these things are kind of more interesting. You can't look at them by hand as much. And the dimension is D. D is also going to be large in this case. So we're thinking of hundreds of dimensions maybe, or maybe thousands of dimensions. D could be larger than n. This is fine here. I've just drawn it. I typically draw things with n bigger than d. I like to think the data size is growing. And we talked about Monday that you can use the SVD or PCA to find what's this say best rank case so subspace, and so this would technically be this matrix A, which is also going to be, this is also going to be an n by d matrix. But I can write this, one option here was to write A as this decomposition into U, S, and V transpose. And if I look at the first K columns here, these are the top K left, so singular vectors. Okay, so if I look at this, the coordinates here, this gives me K coordinates for every data point, right? Recall, this is one data point AI. For each data point, I'm going to get K coordinates. This basically gives me a K-dimensional embedding of this high-dimensional data point, from thousands of dimensions down to only 2 dimensions or 10 dimensions. And these are the best in some sense, that if this subspace, call this subspace UK, then this is basically the equals arg min out of all U, where the rank of U equals, or that has K dimensions of, let me write it this way, as the sum AI and A times AI minus the projection onto UK AI squared. Okay, so if I want to minimize the sum of the squared distances from a data point A onto a subspace, right? So this projection is this distance here. This is AI. This is, if this subspace here is UK, then this is the projection onto UK of AI is this point. And if I look at all those distances, the closest projection distances, and I add up the sum of the squares of those distances, then UK, the subspace defined by the top left k singular vectors here, is the best choice here. It's minimizing the sum of those squared distances. Okay? So this is a nice property to have. What we're going to talk about today is like a different way of defining what I want by optimum. This is saying, you know, I can have some things that are large as long as on average they're small. We're going to look at a different property today where I'm going to think of defining, so I'm going to define some map mu, which goes from RD down to R, I guess we'll use K here. Okay, so down to K dimensions. And I want to have the property that for all AI, AJ in my data set, and some error parameter epsilon, which is greater than 0. So think of, say, this is about, say, 0.10. So like it's 10%. Then I want to have the property that 1 minus epsilon times AI minus AJ. So if I look at the distance, let me just write this up. Okay, so if I look at the distance after I projected all the data points, so I want this to hold for all pairs of data points, so all AI and AJ, and I look at the distance between them, okay, after I projected them, that's going to be about the same as what the distance was so before I projected them. Okay, it's going to be within 10% error if epsilon is going to be 0.01. Right, so it's not going to be 90% smaller or 110% of what the previous version was, right? So all distances are approximately preserved, right? So this means that if I'm doing nearest neighbor search and I actually don't know what the right threshold is onto my nearest neighbor, right? I don't know how close the nearest neighbor is going to be, but I know that I preserved all the distances within a 10% factor. Right, so I've still preserved approximately the nearest neighbors in some way, without knowing what the scale of the nearest neighbors are going to be ahead of time. Okay, whereas with the PCA approach, some of the points might get greatly distorted because they happen to have a large component away from the subspace, the best subspace I found, and so their nearest neighbors are completely distorted, where other ones are basically preserved. Okay, so it's a different sort of property, and this one says it has a guarantee that the error is for no point is it larger than this amount. Okay, so I want to project to a lower dimensional space where I can guarantee that all the distances, all the pairwise distances, are approximately what they were before. Okay, and what's amazing is that you can actually do this. And it turns out that you do it just by choosing stuff randomly. Just works, and you basically can't do any better than that. Okay, so it's all kind of cool. The downside is that the scale of D and K need to be pretty big for this to actually make sense, for it to be practical. But nowadays there are really big data sets that you get from like at the size I have at Google and Facebook, where the regimes, the sizes where you need this to happen actually occurs. And so this is actually stuff like this, and a couple of kind of more advanced techniques we'll see kind of are actually super, super useful. Okay, and the technology is going to be similar to like locality-sensitive hashing. A lot of the similar math is behind what makes this work. So how do we create this map? Okay, any questions on what this means? On how to understand this? So I've got some data points in RD. And I'm going to define some map mu, and then the same data points are going to wind up in some lower dimensional space, and this will be RK. Okay, they don't have to be close to what they were before. Where they were, it's a fundamentally different space here. It's a different representation of them. But if I look at any particular pair from before, this pair, maybe it shows up here, and this distance is approximately, this is maybe, and this is, right? So the distance from here is going to be preserved about the same as the distance afterwards. And this will be true for all pairs. Okay, and it turns out you can do this so it's going to be a randomized algorithm, so with probability greater than 1 minus delta, setting k equals to approximately 1 over epsilon squared log n divided by delta. Okay, there's some constant factor in front here. It's probably about 2. Okay. Okay, so it depends on the size. This is where the size of A equals n. All right, so actually it only depends logarithmically on the number of points and was independent of what the original dimension was. These are also kind of things which are kind of cool that you can do this, although it depends not great on epsilon. Okay, so we'll see what this means. It means like if epsilon is 10% error, this term is roughly 100. If it's 1% error, this term is like 10,000. Probably one closer to 1% error than 10% error in a lot of applications, which means that, usually k needs to be about 1,000 for this to actually make sense. But if D starts out as a billion, then this is a huge, huge win. Okay, so this is the premise. So how to construct mu, right? This map from RD to RK. All right, so so it turns out we're going to construct this one coordinate at a time. Basically, I'm going to say that mu of A is going to be a vector mu1 of A, mu2 of A, mu k of A. Okay, so I'm going to construct this vector one coordinate at a time. And so let's focus on mu j of A. So I can choose this independently, and then I'm going to kind of do all k of these just independently the same way. Right? So I'll just do one. It's going to be a randomized approach, and I'll independently do the other ones. Okay? So mu j is going to be defined of A is actually going to be a dot product of A, this vector A, which is an RD, with U, J. So Uj is a uniform over, right? So this means that Uj so Uj is going to be a random unit vector, and so this is basically it. Okay, I actually need to do 1 over square root k in front here just to make sure that I get the scale right. But this is the whole construction. Okay, so we pick a random unit vector, and if you remember, we can construct uj as a multivariate normal distribution. Yep.
Sorry, in the notes it looks like it's scaled by square root of d over k.
Okay, let me, yes, that's right. So thanks. Yeah. So okay. So I'll actually go through the math and we can check. Yeah. So we'll actually, the argument of more or less why this works, or at least why it gets the right expected distance, won't be too hard. Kind of it's a little tricky, but not too bad to actually show why you only need 1 over epsilon squared terms. And I've got like a 1 or 2 page proof. I think one of the links from the first lecture actually added that in there. It's almost an application of the Chernoff-Hofting bound, but you need something with chi-squared random variables instead. But aside from that, the proof is not too hard. The original proof of this was hard, but people have worked at it and gotten this much simpler over the years. Okay, so how do we construct this vector again? We can create. Actually, we can say that there's this Gj, which is this. I can draw a d-dimensional normal random variable, and then I can construct Uj equals Gj over. So this is a Gaussian random variable, and I can just normalize it, and this works. Remember, and we can construct these using the Box-Mueller transform. Right, so we can construct these using the Box-Mueller transform. It turns out that if you normalize this correctly, this has the expected norm of this is going to be 1. So it turns out if you don't normalize it, things basically work out okay. So I can actually plug these directly into there instead. I can use Gj instead of Uj, and everything works. The constants might be slightly worse, but the difference is pretty small. Okay. Okay. So let's. Yeah. So what I want to show is that. So this is okay. Actually, let me say. Okay. So there's a different way of thinking about this as well. That my goal is to get a matrix B, which is n by k, which is going to have the property which I want, that all the pairwise distances are approximately the same as from this matrix A, which is n by d. And so all I need to do is create a d by k matrix here, S. And basically what this dot product is doing is I'm basically multiplying every, right, so the first coordinate, so this here is basically Uj, the first coordinate here, and I have k of, or this one is U1, right? And this one is UK, right? So each of these are these unit vectors which which are define this map. I can put the square root d over square root k inside this inner product. So assume I did that properly. Then I'm multiplying each row by each of these, and I'm going to get these new coordinates here. Okay, and if I don't worry about normalizing, then these I drew each of the coordinates here independently, which means actually if I use instead the version with the Gaussian random variables, then I can say that each Sij is just going to be with the appropriate normalization, square root d over square root k. Or I can put that inside here if I want. So I can draw Gaussian random variables, appropriately scale them, put them in a matrix, which is, this is going to be a d by k matrix. And I multiply A by this D by K matrix, and I get a smaller dimensional matrix. And all the approximate distances between the pairs of points are preserved. Okay? One thing to notice, if I kind of pretend to include the all zeros vector in here, this basically still works. Just increase n by 1, which is not a big thing, which means it will also be the all zeros vector still here, which means that the norm of every one of these vectors is also approximately preserved. So the norm of a row here is going to be approximately the same as the norm of the row here. Okay, so this is a very simple kind of operation, and it's a way of reducing the dimension, and it approximately preserves all distances between pairs of points. Again, this works in a regime where like d is millions and k is like in the range of thousands. That's when you'd want to use this. Just because you're not going to have very strong guarantees on the error preserved if you go to much lower dimensions. You can go to 100 or so and you can see what happens, but this isn't going to really, this technique is not going to get you to a way where you can like go down to 2 dimensions and draw a picture that you're really going to trust it's doing the right thing. If you really need to go down to that, you're going to use PCA or one of the derivatives of this that we'll talk more about next week. Okay, but if you just have a really large data set and you don't know what to do with all the dimensions and you don't think they all matter, and maybe you want to run like lasso or something on this because you don't think you need all the dimensions, but you're like, well, I actually don't want to worry about running lasso with with d being 1,000,000. I'd rather reduce it first by a very simple operation, right? And I can do this first, and this is fairly efficient to do, and it reduces down to a much smaller size, and then my downstream algorithms run faster. Right? So, okay. So let's try and explain why this is working. And I want to show you that it gives the right expected value. Okay? So, and I'm going to argue about the norm of a single point instead. Right? So instead of, the guarantee is that, I don't know, my pen stopped working. Okay. Do a quick chart. So what we're going to show is that I said that I want to preserve all these pairwise distances. A simpler way of thinking about it is, and this is how the analysis will actually work, is that I could think of all the pairwise distances as actually n choose 2 actual individual vectors. Right? If I look at ai minus aj, that's another d-dimensional vector. And I'm going to preserve the norm of that vector. That's equivalent to the distance. And because this map is going to be all dot products, it means that it's a linear map, which means that if I preserve on the individual, if I preserve the a minus aj vector approximately, then it will also be preserved if I consider the projection of the individual points, right? So it's going to be enough to show that I preserve the norm of an individual vector. And then I'm going to use the union bound, right? If I look at this bound here, I'm going to have a probability of failure, which is going to be typically in these Chernoff-Hopting bounds, you have like a 1 over log 1 over delta probability of failure. And I'm going to have an n squared inside of here. I'm going to check over n squared pairs of vectors. If I put a square inside of a log term here, actually you can factor that 2 out in front, and that's why I said there's about a factor 2 out in front here. Turns out the other parts don't give too high of factors in practice. Okay, so we're going to try and show that an individual vector is going to have its norm preserved. And you'll probably trust me that it's going to look something like an application of a Chernoff-Hopting bound. I'm not going to go through that, but I'm going to try and show you that the expected value is preserved. Okay, let's see if my pen starts working again. Okay, so I want to show that. Okay, let me try and something else here. So what we're going to try and do is show that the expected value of the norm is preserved, and because we're going to average, we're going to show that the squared norm is preserved, and that's why I needed the 1 over square root k in this term. We're going to show that the expected squared norm is preserved over what's effectively the average of k of these things. So I just need to show you that one of these projections, one coordinate, approximately preserves the right distance. Okay, let's see if this works. Oh no, so. Oh, okay, do you have a pen?
Let me check this chart.
Says it's connected, it's just not writing. Okay, I'm gonna try and reopen the notes tab.
Well, it has 10% with that.
Well, so let me try this one thing here.
This has 10%, I don't know.
Okay, that should be.
We can charge these in the meantime, right?
Sure, yeah, that's probably the issue. I think I charged it last week. Okay. See if this works. Oh, okay, good. So we're back. Good. Okay, so what I want to show is that the expected value of mu of A is going to be equal to A. Okay, and in order to show this, I want to show that the expected value of the norm, and actually the squared norm, sorry, the squared norm is the same, which means that this is going to be square root d, actually d over k. So I'm squaring, actually let's write it out this way just so it's clear. U right, so this is a one term of, it's equivalent to look at one term of this squared, which means it's d squared, it's actually square of square root d, which is d, and square of square root k, but I'm actually going to look at one term. I don't want to take the average. So basically I want to show that d times uj, so I'm going to set effectively k equals to 1 here. So I want to show that this is going to be equal to the original norm square root of A. Okay? So basically I want to show that in expectation, the squared norm of A when projected onto uj is going to be approximately 1/10 of the original squared norm. Right, I'm increasing by a factor d here. Right, so what's going to happen is I can think of having my coordinate axis here. This is going to be RD. I'm going to have a point A here. And I'm going to pick a random dimension, uj, and I'm going to project onto here. And I'm going to look at this length here. This length is going to be a dot uj, right? In fact, I want to look at its squared length, and I want to compare the squared length to this vector, the squared length here. Okay, so what does this kind of look like? We know that this is an orthogonal projection onto here. And this is 1 out of d. This is a d-dimensional space. We know that if uj happened to be the coordinate axes, right? So let's say the ej is going to be the vector which is where this is the jth coordinate is 1, right? So this defines the coordinate axes. If instead I picked one of these coordinate vectors, ej, then it's pretty easy to analyze because I know that a squared is going to be equal to j equals 1 to d of a times ej squared. Right? If this is exactly the Pythagorean theorem. Right? So by the Pythagorean theorem, I can decompose the squared norm into the projection of the squared components upon some sort of orthogonal basis. Right? If I pick the coordinate axes instead, right? So this would be E1, this would be E2, and there are D other things coming out here. So if I chose this one, then on average, there are D of them, and I know they add up to this, so if I picked a random one, it's going to be on average 1/10 of the total squared norm. And this was the coordinate basis, but if I picked any orthogonal basis, let's say I picked any orthogonal basis, let's write this one in blue. So if I picked any orthog basis, u equals u1, u2, uj up to ud, right? So all these are going to be unit vectors or orthogonal. I can plug uj into here too, and then if this direction I picked happened to be one of these, and it's that for some orthogonal basis, so that means the expected squared norm from the contribution of any one of these is again 1/10 of the total squared norm, which means I get this property that I designed. If I multiply it by d, then I get the expected value of it is exactly the squared norm, and I have all these independent random variables which are all give me the right expected value. Right? If I put the 1 over square root k in front, then that means I'm averaging over k of these, and so I just get concentration of measure. Okay, so is that, for those who are mainly following, you kind of get the gist of it. Because I pick a random basis, it's out of d, it's going to give me roughly 1/10 of the squared norm. So if I multiply back by d, it's an unbiased random variable. Every time I do a projection, I'm getting a smaller norm, and it's on average 1/10 of it. Okay, so that's basically the whole proof why the expected value works. If you have random variables that are independent, they all have the right expected value, concentration of measure works really well. So I want to quickly say 2 extensions. One is something called an oblivious subspace embedding. Okay, so this is saying something stronger, that I'm that I'm going to guarantee that I want to do this construction where this is B, this is A, and this is this S matrix again, and this is the K dimensions here. And I want to guarantee that for all X in RD, a stronger property holds, 1 minus epsilon okay, so if I multiply X by this matrix, and I do the same by B, I'm going to get approximately the same squared, I'm going to get approximately the same norm here. This is basically the property I need to guarantee that that if I run regression on B instead of A, that this is going to hold. Okay, so I need a slightly, this is a slightly stronger property than before. Instead of looking at basically the n squared different directions corresponding by pairs of points, I'm now considering any direction x. Okay, so this is stronger than before. Instead of only n squared different directions, I now need all infinite possible number of directions. It turns out you can get this to hold with k equals d over epsilon squared log 1 over delta. Okay, so this might seem a little weird. I need to make k is now larger than d. So I'm going to a larger dimensional space. But the advantage of this is that there's this kind of this is independent of n. So this will hold even as A and B get larger and larger. I can map to this space and know that this space is going to be sufficient. I'll try and explain in the context of streaming algorithms next week why this is a little bit interesting. But this is a stronger property, and you need something larger than D for this to work. But you can use this in a way to do linear regression in like a streaming setting, which we'll see next week. I'll just pre-process this here, and then there's a count sketch variant of this, and then I'll stop so we can do our group discussion, where instead of this matrix S, which remember was D by K before, and before what we did is we could fill each of these, which would be basically this could be a Gaussian random variable. I can do something where I instead say have my matrix S be sparse. And in a very particular way, what I'm going to say is that for each column in here, it's going to be all zeros except for one item. And this item is going to be a -1 or a +1, uniformly at random. But I chose, for each row, I chose this element at random. So I chose, for each row in this matrix, I chose one at random, and I made it randomly a -1 or +1. Okay, and now I can multiply this in the same thing. I multiply this by A, and I get a matrix B. And it turns out most of the same properties hold. For this setting, I need D squared instead of D over epsilon. But I also get a lot of properties kind of preserving the pairwise distances. It's not quite as strong. You don't get quite as strong results. You get a version of this stronger result, but you need more dimensions. For doing faster JL, there are other techniques. But if I want to preserve regression, this is faster because define this matrix as a hash function. Each dimension basically hashes to one of the new k dimensions. And so I can just store a hash function here, and I randomly add or subtract it. And if you remember the count sketch from the streaming section, that's basically doing the same thing, which means that to multiply this by the matrix A, I basically, each row, I translate each row here, I basically pick, actually, there's something I have to, it's better to look at this in the transpose. I'll try and fix this when we talk about the streaming section. But basically, I can do this as fast as reading the matrix A. So I can kind of do a transformation on A and reduce the size of it basically as fast as reading it. And if it starts out really enormous, I can get down to a manageable size, like thousands of dimensions, as fast as reading it, and then I can do my better analysis afterwards. So I'll just give you, this is just a preview of these things. I'll put these in better context. I think it's better to transpose how you think about the matrices when you do these, but we'll see how that works, and that'll be cool in this streaming section. We'll see other techniques for very large scale versions of PCA there as well. So I'll stop there. Okay, so for the rest of the time, we're going to split up into groups, and kind of you're going to discuss amongst your groups and give yourself feedback. This is roughly how we broke it. So each of you have a group number, and we've kind of given you some sort of category. I was not the one who assigned the categories, so and if you have a single person group, then it means you just have your name up there. And what you should try and do is this column, we're going to have meet along this aisle with the bottom side towards the front of the class and the top side towards the back. This column will meet along this aisle. This will just help you organize into groups. Then you can go find places to sit and discuss. And I'll kind of walk around.